Hey, welcome to Munro Live. I'm Paul Turnbull. I work for Munro Associates, an engineering consulting firm that does teardowns and benchmarking of all kinds of products. Today, I'm here with a couple guys from GM, Ed Kaiser and Pat Lencioni, and we're going to talk about this front drive unit from the Equinox EV. Ed, you want to go ahead and introduce yourself?
Sure. My name's Ed Kaiser. I've been with General Motors for 25 years. I'm the motor technical specialist for the traction motors.
And Pat?
Yep. Hi, I'm Pat Lencioni. I'm the assistant chief engineer for the crossovers and SUVs applications of the EV systems. I've been with GM for 37 years, and I'm happy to be here. Thank you.
And Matthew?
Yeah, Matthew Lawrence. I work here at Munro Associates as well with Paul. I've been doing electric vehicles for about a decade now.
So one of the things that we noticed about this drive unit came from the Equinox EV, but this particular drive unit is used not just in the Equinox EV, it's in the front drive unit, but it's also used in the Blazer, as the front drive unit, and the Honda Prologue, the Acura ZDX, the Cadillac Lyriq, the Cadillac Optiq. That's what's out right now, and there may be others that are coming soon with this drive unit. If you add up all of the production numbers, all the sales numbers for the vehicles that this drive unit has out there, you get a number that is second only to the Tesla Model Y. So right now, this drive unit is in more vehicles than any other drive unit, electric drive unit, other than the Tesla Model Y. And that, by the way, Tesla also has the Model 3. I think the sales of this, when the sales numbers come out for the third quarter, are going to end up totaling equal to or maybe even more than the Tesla Model 3. So, so far, no other auto company has done that. And so it's nice that this drive unit is having that kind of success in the market. Before we go any further, I need to do, for full disclosure, I think the viewers of this channel know, I previously worked at General Motors. I was on the team, and I'm very proud to be a part of the team that worked on this drive unit. So I'm not an independent reviewer. Certainly some of the things that I worked on are a part of this motor. And if I point out some of the issues, those issues are things that I share blame for. So that's a part of the whole deal. So let's talk about this with you guys. The idea here is that the Equinox gets 319 miles of electric range, and it does that with an 85 kilowatt hour battery, which is a relatively small battery for that much range. The Equinox has average aerodynamics. The only vehicles that do better in terms of electric miles per kilowatt hour are vehicles that have spectacular aerodynamics. Mm-hmm. So if you're able to get that range without amazing aerodynamics, it says a lot about the efficiency of this drive unit. So what did you do to make this drive unit so efficient?
Yeah, that's a great question. When we talk about efficiency, oftentimes people talk about the motor efficiency, and you're correct, the motor has really good efficiency. This is one of 3 motors in a family. So this is our middle size motor. It's 180 kilowatts, a little over 350 newton meters of torque. But when we design the motor, we look at how the customer is going to use it, in particular all the drive cycles that they're going to do. And that's a combination of performance cycles, durability, and how they're going to experience, the vehicle. with this particular motor. So we take those cycles and we basically start with like a seed motor. And when we are optimizing the machine, we're making thousands of iterations of the motor and its design. And we want to find the best motor for the applications it's going to go in, because as you mentioned, this goes in many applications. So we're trying to find the best optimized motor for the actual drive unit. So the motor has great efficiency, but the drive unit is also a big part of that. So how fast we go, the gearing, the spin loss. So we're trying to find not just the best motor, but the best system at a drive unit level for the vehicle.
So you're saying each unit or each vehicle has a slightly different version of this motor or drive unit?
Actually, we're trying to find a motor, a common motor for this size. So that's why we have 3 sizes of machines for different architectures and placement in the vehicle.
Well, I mean the gearbox, I should say, to be more specific. It's slightly different for different vehicles.
I can field that question a
sure,
little bit. Sure. Yeah, the base motor itself is common,
Yes.
but we do have 2 different gear ratios. We have an 11.59 and a 9.87. So we are able to customize it to the vehicle applications, to the performance that the end customer needs, to our calibration performance attributes. So Paul, I'd add that the Cadillac Vistic and Celestiq, as well as the Buick Electra, are 3 other vehicles that currently have this. So you're right, this has such a broad scale worldwide. This goes into our North American domestic market, as well as all of our export markets, Europe, Asia, Australia, South America. So we have a global footprint for the technology here, and it's a scale that is just a really great product to work on, and get that bandwidth worldwide.
That is how you compete internationally, by getting a common motor and put it across multiple platforms, and I'll give you the volume you need to do a custom design like this one. So one of the things that's immediately obvious when we look at this motor, first of all, it's incredibly small for 350 Newton meters of torque and over 220 horsepower. 220
horsepower for the base.
For something this small, I mean, you can just pick it right up. You try that with a 220 horsepower engine block.
Gas engine, yeah.
Yeah. By comparison, even among electric motors, this is a BYD stator. So this is a 320 Newton meter motor that does 200 horsepower. So it's a little bit less powerful, but significantly, this is like 14 kilograms, this is 19 kilograms. There's 5 kilograms of difference between them, of just steel and copper. I mean, that's not only package and weight, but it's cost.
Yeah, cost is a really good point, because people like to compare the cost of the motors and such. When we're designing the system, and back to your efficiency comment, our goal is to make the vehicles affordable for our customers. And to do that, we have to look at the battery cost and the efficiency. So there's a case to be made where a larger motor may be more efficient, may cost more, but to the end customer, it's going to make a more affordable vehicle. So when we do the optimization for the motor, we're considering the total cost.
And how did you optimize for the thermal challenges you probably ran into? Because I imagine something that small and that powerful definitely gets pretty hot.
Yeah, so this is our 9th iteration of the bar wound technology.
Okay.
We used to use motors similar to that back in over 20 years ago, where they're wire wound. And one of the major disadvantages of that motor is getting the heat out of it. And the longer we make the motor, the harder it is to get out. But with all the round wires, it's hard for oil to get inside. So with the bar wound motors, we're oil cooled, like most others are doing. But the oil is able to flow through the windings, and we're able to to get the heat out of the motor so that we can get the density up. Because our other metrics that we look at are torque and power density. And you're right, we can have high peak torque and power density, but if we can't cool it, then can't really utilize it. So we're oil cooled. We have oil running through the rotor as well. But mainly the stator technology that we've chosen allows us to get oil inside and keeps it good continuous performance out of it.
Now, other companies have put oil channels actually in the stator and using forced oil to high pressure oil down straight through the stator. And you've taken a different approach where you're just slinging oil up into the top of the casting. And then this actually has ended up in the car, it's like this.
Yes.
And that oil just gathers here, and then it just rains down through these channels using gravity fed. From a cost perspective, how does that what is the advantages and disadvantages of this type of cooling system?
When you use the systems that have more direct streams of oil, especially if they're going to come out not using gravity to help them, it's very tricky to engineer so that they will perform over the whole temperature range. So as you can imagine, the oil gets thicker and when it's up to temperature. So we want to make sure the oil can hit the windings to cool the motor. So that's just trade-offs. It can be done both ways. We prefer in this architecture with how we were supplying the oil to drop it down on top and let it flow around the winding.
And there's no issues with like gradient if you're going up or downhill?
We actually simulate that. And part of the design is not to have it so far so that when we're on a grade, it misses the winding. But yeah, it's a great question.
So there's really three things that I loved about this motor. The first is that efficiency. The second is the amazing power density of the motor itself, which not only gives you all the advantages of weight savings, and lower inertia, but also that's how you compete cost-wise with guys like this who have lower labor cost. But the third thing that I absolutely love about this drive unit is what's all up on this board here. On top of this drive unit sits a 5-in-1 power electronics box that has a DC to DC converter, an onboard charger, the computer to control everything, and 2 inverters and a power distribution box. Power distribution on DC to DC.
5-1.
The 2 inverters would be in the all-wheel drive versions where we power with the with the rear.
And so if you have a
drive
front wheel drive, you can just decontent and have only one inverter.
Yeah, the single inverter.
And if you have 2 motors, the all-wheel drive version, the second inverter is up front, and then AC lines go to the back.
Correct.
So all of this makes that, so you have this thing in, how many cars is it?
10.
10 cars.
10 different vehicles.
10 different vehicles. So the integration challenge is amazing, right? So normally you have to find spots for all this stuff.
Exactly.
If you have it all in with the front drive unit, you drop in the front drive unit, 80% of your vehicle architecture is handled with one part. So yes, kudos for this. The 5-in-1, by the way, this is something that BYD is kind of advertising that they invented or something. You guys have been in production with this for years. But yes, that combining all these power electronics components together with the drive unit is the secret to being able to integrate this drive unit into 10 different vehicles.
Were you able to find efficiency gains also by having everything so close, since you have less copper and less distance between the DC links?
Yeah, the elimination of the cables, the combining of those modules all into one, we took probably 40 to 50% of the volume of the previous footprint all into one. And so that allowed us to get such scale for the different vehicles. Of course, we had some spirited challenges even with the vehicle integrators, even with what we had, but that's always what we enjoy to do as engineers, right? So, yeah. But no, we have the single inverter, the dual inverter. We also have for the charging RPOs, we have a different variant for the exports that we do for the domestic single phase versus 3-phase charging. So, and also to package with high voltage and low voltage batteries. So the IPE itself, as we call it, integrated power electronics, we have about 8 different flavors of those. And again, for that global footprint that we work on. So,
what was the most challenging thing in combining everything into one unit?
I think the most challenges were just, essentially, basically getting, all those modules into one tight space and preserving the integration around it for the vehicle. So, went through a few iterations, and we worked with our suppliers to ensure that we were able to, meet the performance and, meet all the cost challenges that we had. So,
yeah, in general, our biggest challenge was the complexity of what we were trying to do. Mm-hmm. Previously, we would focus on, a vehicle, more of what we'd call a point solution. Even in our motors, we'd have a motor for this vehicle or 2 motors for, this drive unit, for instance. But this time around, we wanted a complete, platform family approach. So even on the motor, it may not, unless you put them side by side, it may not be obvious that it's a family of 3 machines. We have an induction and 2 permanent magnet machines, but we're scaling radially. So if we look at our smallest machine, it has 4 conductors per slot, and then we go up to this motor here, we have 6 conductors per slot, so we have another row of hairpins around it, and then we go up to the motor used in the Silverado EV, for instance, it has even another row. So we're scaling the motor radially, which is something that is kind of unique for our approach here. But the complexity is the challenge that we have but we're solving that with having, a flexible strategy that we can manufacture.
So when we talk about slots, when you describe a motor, and we're talking about inside the motor, each lamination that builds up the core has these slots where the wires go. This is a typical 48 slot design that this particular one is from a Hyundai. Ford uses the same winding pattern. VW does. This one, in addition to being scalable from the number of wires in the slot radially, you've chosen to go with 96 slots. Everyone else is at around 48, so double the number of slots. I think that there's a couple other examples that are at 72 slots. And so what was the advantage of going this way? Because you have twice as many of these hairpins to deal with.
Yeah, that's great question. Back to the efficiency. We were looking for a motor that would also have, very high power density. So we got some benefit there. But just from an efficiency standpoint and how we operate, oftentimes, in motors, we like to talk about how fast they go and their maximum speed. Well, as we go up in speed, our spin loss, in the whole drive unit starts to hurt us and hurt the range of the vehicle. But we spent a lot of time at the medium load, light load even conditions when we're driving, a lot of energy spent there. So we went with smaller conductors. And when we did our optimization and trade-off, the biggest challenge was manufacturing. So at GM, we have a full prototype manufacturing lab that has production equipment in it. And that was a significant part of the development of the motor was, to put all that together, to make all those wire forms and to weld that and make it manufacturable. Because from the design of it, the electromagnetic design of it, it was great for our performance for this application.
So returning to that efficiency discussion, Was there anything else that you did other than the optimization to get the efficiency numbers?
Yeah, one thing to note is these are interior permanent magnet motors, and inside, what that means is inside the laminations we have neodymium iron boron, like sintered magnets basically, that are inside the rotor. We chose that for this machine and the larger version of it for efficiency. That's a big driver. It's true, there's lots of news about magnets and, supply of magnets out there. Well, one great thing about General Motors is we have really good supply chain folks, and they've been working with us for a couple years now, actually, to get domestic magnet production going in the United States. And we have 2 suppliers we're partnered with. We have MP Magnetics, and we also have EVAC. And they're basically putting their plants in right now for us to have domestic supply of magnets. But from an efficiency standpoint, we did make a change to improve the efficiency of the motor. And what we did was our sintered magnets that go inside here, which you can't see, were basically 4 blocks, for instance, rectangular shaped blocks. We have cut those into sections, and they get processed and glued together. So from a manufacturing standpoint, because we make these rotors inside General Motors, right next to the drive unit assembly line. So for us to have minimal impact to the assembly of the rotors, to them it's transparent. The magnet's the same shape and size overall, but it's actually 4 magnets put together in each one of them that they install. And that allowed us to reduce the losses in the rotor. It allows us to operate cooler, but most importantly, increase the range of the vehicle. So that's just one example of ongoing improvements we make to deliver better performance for the customer.
So you did all this in a virtual environment first, right?
Yes. So we're able to do all of our engineering, which you would expect through our analytical tools that are some that are developed in-house, especially our optimization processes. But we also do validation of the motors and drive units. We do both virtual and physical hardware, and the power of the virtual engineering and virtual validation activities is we can vary more parameters than we can by just taking a few motors off the line and testing them. So that allows us to run more simulations and verify that the customer won't have issues in the field.
So I assume too you were able to see whether if having a segmented magnet did cause any issues or any changes as well, right?
Yes.
Or
yes.
how many segments you could do potentially.
Correct. We wanted to make sure that we wouldn't have any demagnetization or anything on the rotor. The magnets, it costs more to make smaller pieces and put them together.
Right.
This is a good example of while the rotor cost would go up, the benefit of that change is still positive for the end customer. Because we look at it as a complete system efficiency, because battery is a significant cost factor for the vehicles, and we know everything we can do to make things more efficient will help that.
Mm-hmm.
Yeah, if you can save $1, you spend $1 here, you can save $10 on the battery.
Yeah.
And that's overall a great trade-off. So this was all going down the same, this motor is going down the same line as the bigger motor?
Yes. Yeah. So we, for the rotors, it's very straightforward. We run them down the same line, and we can make both. But we can also do that for the stator as well. So that was what I referred to for the radially scaled family. So a lot of the wire forms and the forming tool, the press tooling that's making those wires, it's the same between both the larger motor and the smaller motor. We have some additional wires that we put in, and we have some differences in the number of parallels that you mentioned and how they connect with the connection rings. But because we can keep the wire the same size, we're able to reuse a lot of the capital and efficiently run the line. And it's another reason why we like this style of motor where we have hairpins, because I'm sure you've done videos on other types of winding that would be continuous, for instance. But we want to be able to have a motor that we can scale in a couple dimensions. And this allows us to use our same manufacturer forming tooling. We just have longer wires. And in the case of the larger motor, we have a few additional wires, and then we insert them and put them in. And the other operations are tooled so that we have a flexible line, basically. So we can make two pretty significantly different motors, different turn counts, different size on the same line.
And all of that's taking place in the same location as the whole drive unit assembly?
Stators are done at different facilities, and the rotors, though, we decided to take a kind of a clean sheet of how we manufacture and the supply base, and we determined that a rotor and a stator don't have to come from the same plant. And when we looked at the rotor, there's all these operations that we do in here that are very similar to what we do today in production. And so we locate the rotor assembly line right next to the drive unit line. And that way we don't have to ship it to another location. We don't have to worry about the magnetization, because plant safety is a very important factor here for a motor that's magnetized. So we'd like it to be magnetized and put into the drive unit in the shortest amount of handling as possible.
Yeah, you don't want to accidentally have stuff attracted to the magnet. So this is a 220 horsepower motor drive unit, but in some applications, performance applications like the Blazer, or bigger applications like the Vistique, this isn't going to be enough. So what do you do with that?
Yeah, Paul, good point there. With the larger vehicles, the 180 kilowatt machine actually becomes the secondary drive unit in those vehicles. As we talked about with the family of the 250 kilowatt permanent magnet, that becomes the primary in the rear of the vehicle, and this is the secondary in the front of the vehicle. So we've been able to tailor to the vehicle performance requirements, to the customer demands, a product that will basically scale from call it a base model of 220 horsepower to over 600 horsepower in our performance applications. And we're also, one of our enablers there is, again, we do have the two different gear ratios that we do have on the X76 unit here, the 180 kilowatt. Like Ed mentioned about the VDDV tools, or the virtual tools that are used on the motor, we also have a very great depth of gear technology and gear expertise in-house, where we also use our virtual tools to look at our microgeometries and customize and optimize those across these 10 vehicles. Of course, we don't want to have gear meshes unique for all 10, so we do need to find the best blend that can serve all purposes. Of course, some of the vehicles where this is a secondary machine, the duty cycle is not as demanding as what it is when it's a primary drive unit. But we were able to, whether it was some fates width, some microgeometry optimization, to address any structure-borne, airborne noise, as you know, without an engine in the vehicle to mask noise, the sensitivity of the drive unit gear noise can be substantial in vehicle. And so we've been able to use our virtual tools, duplicate those on hardware, and bring an optimal system with minimal noise, to all of our launch products and what is in the marketplace today.
So when you have, it's really a huge difference between being the primary driver in a vehicle like the Equinox,
Yeah.
versus the loading on it, the duty cycle for everything, versus being the secondary drive unit, where it's actually off a lot of the time.
Exactly.
And so that secondary drive unit is going to see an entirely different kind of loading. And that's also where the segmented magnets in here give you a huge benefit.
Yes.
Because when it's off, the magnets don't have the eddy currents that are generating losses when it's just spinning. So all these things work together to create something that is going to work really well in all kinds of different applications.
Exactly.
So that's really amazing. So we mentioned the 10 different applications. A 220, I drive a Chevy Bolt. That's my current driver. So does Matt.
Yeah.
And so we're kind of curious. It sure would be nice to get this technology in a Bolt. Can you guys give us a hint on whether that's coming up?
Well, we are excited that our 10th vehicle will be the 2027 Chevy Bolt. That will be launched later this year. It will use the same drive unit here at the 180 kilowatt machine. So yeah, it really kind of rounds out our portfolio. Again, from base models to performance, we are able to scale and bring these offerings at cost efficiencies across all of our portfolio.
Okay, it wouldn't be a Munro video if we didn't point out some things that maybe could be done better or save you some money.
Sure.
So one of the things that you guys do, along with just about all the legacy OEMs, is you include a standard automatic transmission park pull mechanism. So when you put the car into park, this, which is sitting here, this cog gets held in place like this. And of course, there's a little bit of wobble there. So you can feel it in your car. When you put it in park, it sort of drifts back a little bit. Exactly the same way that every automatic transmission has worked since the 1920s or 30s. You guys have this in production. It's not a very expensive thing. You're making them by the million. It makes perfect sense to put it in. But you also have an electrically actuated parking brake. And whenever the car senses that it's on an incline, you actuate the parking brake. And so other companies, who shall remain nameless for this, but they choose to just use the parking brake all the time. So it's just, for you guys, it would be literally a software change because you already have the mechanism in place. Actuate the parking brake every time, and you can eliminate this. There's a question about redundancy, and the way that the other companies have handled that is by taking the front and rear, left front, right rear, and making it a separate circuit, separate system than the left front and right rear. So you get two separate parking brake, so you have redundancy, and you can eliminate $25 of cost and provide the customer with a vehicle that when they put it in park, doesn't move at all, doesn't drift, doesn't rock back and forth. Arguably better. So there you go. Free idea, save 25 bucks-ish, and maybe there's opportunity for more than that. We've been criticized, by the way. I mentioned how, and I saw this on the same thing on the Nissan. Nissan does the same thing. Ford does the same thing. And I talked about how it makes perfect sense to do this as an OEM. You've got the solution. If it's not broke, don't reinvent it. But it has been reinvented by other companies. Maybe adopt what they have. So,
yeah, I guess, Paul, what I'd add there is, we continuously, as you know, benchmark basically all the global competition. This park pull system is in our entire family of the crossovers, the SUVs, as well as the large trucks. So yeah, it is kind of like a tried and true method there. We're continuously looking for cost improvements for sure. always, there's never a day where an engineer is sitting on their hands not thinking of continuous improvement. So these are really good ideas here. And we're certainly, studying, options where we can, whether it's a park system or other areas of system reduction, to look for ways to optimize and, again, bring the best value to the customer without compromising the integrity of the vehicle. So,
which is key, right? We're not taking risks with customers' livelihood with their vehicle.
Exactly.
Is not something that's acceptable. So I understand that, but the drive to save money is essential to stay in business. And there is a tidal wave of competition in this space coming that has to be addressed. And we at Munro reject the idea that somehow American manufacturing can't compete. I think GM and this particular drive unit is a fantastic example of how American engineering is absolutely able to compete in manufacturing with the world, a global footprint of this vehicle, this drive unit. And so, yes, the answer is there are definitely American ingenuity is likely to be able to compete in this world in manufacturing like this with a technology like this. So just wrap up, everyone, thanks for watching Munro Live. We really appreciate your watching. Thank you, Ed and Pat, for joining us here and telling us about this amazing drive unit, and wish you all continued success with this and the next generation. And for anyone who is looking for help implementing solutions like this, just give us a call. Thanks a lot.